Here's question 7 from that spectroscopy review packet. All right. So these are very nice problems, very readable, very complete information. And like we talked about the other day, this is kind of the ultimate spectroscopy problem. There's nothing that you're going to be given that's going to be more difficult than this. This is really like highlights the role that spectroscopy plays. You have a compound, you have no idea what it is. You don't know how many carbons you have, you don't know what elements might be there. All you're relying on is infrared spectroscopy, mass spectrometry, and various flavors of NMR. In fact, in real life, you probably even, if you were to make a molecule, even if you didn't know exactly what you had, you probably had a pretty good idea. You know, if you didn't use bromine, you'd probably know you don't have bromine on your structure, right? If you started with, you know, a benzene ring, you probably know you've got a benzene ring somewhere. So in real life, you probably even know more information. You know at least something about the context. Okay, unless you like, you know, isolate something. You like isolate a molecule from tree sap or something, and you have no idea what it is, but you want to figure out what it is. Okay, in that case, you know, you really do have no context. But let's take a look at this. When I solve these, I always start with infrared. Your methods might be different, but IR for me is the most important place to start because it tells me in very simple terms what I do or do not have. For example, I don't have an alcohol. I don't have a carboxylic acid. I don't have a CC triple bond, right? Tells me right off the bat what I don't have. But there are a couple things I like to do. First of all, I always draw a line, either mentally or literally at 3000. Oops. And nothing creeps above that line. So if it did, anything above that line, I know it's going to be an sp2 hybridized carbon to a hydrogen, or an sp hybridized carbon to a hydrogen, or even further, a nitrogen and an NH, for example, or an OH. Okay, hydrogens connected to heavy atoms appear above 3000. Okay, or very stiff bonds like an sp2 hybridized carbon to a hydrogen, or an sp hybridized carbon to a hydrogen. Those very stiff bonds show up above 3000. And so I like to make a visual note or a mental note. Nothing crosses that line. So here I've got alkanes. That's what I check there. Next, something very interesting that you actually don't see very often is two peaks in this region. Okay, 1755 is pretty high for a carbonyl. And something that high, if it's going to be a carbonyl, which really there's no other things that commonly appear in that 1700 to 1800 region, anything that's going to be that high is going to be an ester. Okay, esters tend to be up there. So I think the other day, the practice problem we did was like 1740 or something like that. So that's probably an ester. But this extra peak, okay, does anybody know what that means when you've got two peaks in the carbonyl region? It's not obvious. Two peaks in the carbonyl region is what you get from an anhydride. Okay, that's a kind of a dead ringer. Okay, if you didn't know that, now you do. Okay, so that two carbonyls or two peaks in that carbonyl region, particularly high carbonyls for that matter, is an anhydride. So really, it's not an ester, but it kind of looks like an ester, right? You can each side of the anhydride kind of looks like an ester. So I'm actually going to erase the fact. I'm going to say it's not an ester. It's high like an ester would be, but it's 2 peaks. So that's the anhydride. Oops. Okay. And if you've got an anhydride, you should also see a carbon oxygen single bond, which is almost always at 1,000. And that's exactly what we see here. So that's our carbon oxygen single bond. So pretty much the only information that I get from the infrared is, well, the only thing that I know we have is an anhydride and nothing else of really any interest. Now often you're taught to ignore things below 1500. And that's okay. Because again, that's the fingerprint region and that can be unreliable. But a CO single bond is so conspicuous in that region that it's something that you can note if you're paying close attention. So we've got an anhydride. That's what that infrared tells us. No significant UV absorption above 220. I imagine that most students will just straight up ignore that. But what that means is that there's no conjugation. Okay. As you get conjugated systems, okay, the longer they get, the longer the wavelength they absorbed. Longer conjugated systems means lower energy, more delocalized electrons. So lower energy electrons will absorb longer wavelengths. So if there's no significant absorption above 220, so nothing in like 240 or 300 or 350, that means there's no conjugated system. Okay, so that's what that means. And I imagine most students would just ignore that straight away, but that's what that means. It's one piece of information. Okay. Now, the IR told us that we have a anhydride, and we don't know what's on either side of those things. But we do know that we've got 3 oxygens and 2 carbons. So as I move to the mass spectrum, I'm going to say, what do I know? Okay. I've got 2 carbons and 3 oxygens, which is 72. Okay. So out of 158, we can account for 72. What's left is 86, and 86 is basically C6, right? It's C6, 6 carbons, and it then C6 is 72. So 72, so 86 minus 72 is 14. So if it's 158, that's like another 6 carbons, C6H14, plus our anhydride. Okay. So very ballpark figure here. I'm not even going to worry about the 71 and the 70 and the 55 right now. If it matters or if I need more information, I might try to go back later and try to decipher that. But for now, I know that I've got about 6 carbons that I need to use. Okay, that's what this tells me. I've got about 6 carbons. Now, maybe there's an oxygen in there. Sometimes different combinations of C's and O's can add up to the same things. So it's ballpark about 6 carbons worth of mass. 6 carbons and about 14 hydrogens worth of mass. Right. So that helps a little bit. All right. Now looking at the carbon-13, probably one of the most critical pieces of information in a spectrum is what you're going to get from the carbon-13. It's just, especially when you combine it with depth, you get some very, very helpful information. So the first thing I see is I've got a peak above or very close to 200. That's going to be my carbonyl peak. Right? Remember, 150 to 200 is a C double bond O. 150 to 200 is a C double bond O. Or above 200 as well can be a C double bond O. And notably, that's not on the depth, right? That's not there, meaning that our carbon doesn't have any hydrogens on it. So that resonates, if you will, with my philosophy or my hypothesis that we've got an anhydride, because those carbonyls shouldn't have any hydrogens on them. So that's fine. Very interesting. There's only 3 more carbon peaks. And I know that I've got about 6 carbons more worth of mass. So essentially there's not enough peaks on the carbon-13 spectrum to account for the mass that I need. Okay, I need about 6 more carbons on my structure. Again, maybe there's some oxygen in there, so maybe it's 5 carbons and an O or something like that. But even if it's 5 carbons left, I don't have that many peaks on my spectrum. And when you see that on NMR, when you see that you've got too few peaks, you should always think about symmetry, okay? Especially because I think I've got 6 carbons and I've only got 3 carbon signals. Okay, so I'm thinking symmetry. That every one of these peaks is actually representing 2 carbons, 2 identical carbons. Okay, they're all below 50. Okay, and 0 to 50 on a carbon NMR are carbons that are only single bonded to carbons. So no, there aren't any oxygens. If there were oxygens, carbons would have to be connected to them. And then they'd show up from 50 to 100. Okay, 50 to 100 is carbons single bonded to O. They don't have any of that. Okay, so I can be pretty confident that I don't have any more oxygens. My mass spectrum does not have an odd parent. The parent is 158, so I can also be pretty confident that there's no nitrogens. Okay, doesn't appear to be bromines or chlorines either, because those also have very identifiable fingerprints in the mass spectrum. So our carbon-13 spectrum actually tells us that there's no more oxygens, and that's very helpful. So I think I've got 6 carbons, and we've got symmetry, and all those carbons are only single bonded to carbons. Okay. Now, really, if you're thinking about, well, what options does that give us? How can we have symmetry with 3 carbons, or with 6 carbons on this structure? Well, you pretty much have to put 3 on each end of our anhydride. So 1, 2, 3, maybe like that. 1, 2, 3. Or they can be maybe isopropyl. Yeah, they can maybe be isopropyl. I'm going to duplicate this. You know, something like this. That we're really out of options here, right? Knowing that we've got our anhydride, and we've got 6 carbons additional to use, no oxygens, they're all single bonded to carbons, and we've got symmetry. You can't really do a whole lot else. So hopefully our NMR can confirm, our hydrogen NMR can confirm that. Oh, we also can look at the depth. Okay, because 2 of our 3 peaks here are inverted, and you've got this handy little reminder that down the opposing peaks are CH2s. Okay, and in fact, only one of our I keep on saying philosophized, hypothesized structures has 2 CH2s. Is that pair, which would be the same as that pair, and that pair, which would be the same as that pair, right? This does not have no CH2s here. So actually our carbon NMR with the depth actually makes it look like that structure can't work. And honestly, there's really no other options for 6 carbons with symmetry on an anhydride. So let's make sure that this is in agreement with what our hydrogen spectrum tells us. Okay, also, by the way, if that's the case, then this, up when it's presented this way with all your depth on the same spectrum, you can't tell if that's an up CH3 or up because it's CH. But with 2 CH2s, our structure basically leaves us with methyls at the end. So those are likely CH3s, or put it that way, those would be CH3s, in which case that peak is a CH3 peak. It's up because it's CH3, not because it's CH. Okay. This would have only up peaks. We had CH3s, which would be up, and CHs, which would be up. So that looks pretty good for our structure. Let's check the, I'm going to copy this and move it down. Now, I'm being very thorough, right? I'm being extremely thorough just to illustrate how much information we actually have. I don't necessarily expect you guys to be so tedious when you're going through this on an exam. I mean, obviously you're going to be crunched for time. So, pick your battles. Okay, to take the lowest hanging fruit and run with it. All right, let's look at the hydrogen NMR. So very nice clean spectrum. We've got a sextet there at 1.17 or so. Okay, and a sextet is one of those patterns that should jump out at you because there's a very common structure associated with a sextet, and it's this. An isolated propyl group. A isolated meaning it's cut off from any other splitting groups, any other groups that will split with it. So the reason this is a sextet is because these hydrogens in the middle would be adjacent to these two. And these three, right? Hydrogens next to 5 will split into 6, the n+1 rule. So these guys in red are causing would cause a sextet. Okay. Now, in theory, this chain could continue. You could have a longer chain than 3. And these would still be a sextet. The thing is that then these would also be it'd be a pentet. And as we add more carbons to this chain, all of the middle carbons become more and more similar. And so if we had a continuing chain like this, you'd start to get a lot of messy signals all showing up in the same region. And we don't have that. So a really nice, clean a sextet with nothing else kind of interfering with it, that's what I mean. That's got to be an isolated propyl group, because otherwise it gets much messier. All right, so that's our pentet or our sextet, excuse me, at 1.7. We've also got a peak here. Very close to what we would expect for an alpha carbon. So if this is indeed our structure, that pair of hydrogens there and that pair of hydrogens there, they should show up around where you'd expect alpha hydrogens to show up, maybe a little more downfield because it's not just a single carbonyl, it's the anhydride. So you've got more withdrawing groups there. So maybe that explains why it's at 2.5. And those would be a triplet, right? Because on our propyl group, it's next to 2. So that works. A triplet, pretty much where you'd expect to see it. And then the only other peak is a triplet at 1, which is our methyl group at the end. Our pink CH3s next to 2. Okay. At the end of our chain, so it should be pretty close to 1, 0.9. That'd be another triplet. So we've got a triplet and a triplet and a sextet. That's exactly what you'd expect to see with an isolated propyl group. So I think that's everything. You can even go further and try to decipher the integrations. If I really zoom in here, and this is where having the magic of technology is nice. If that's what we think to be 2 hydrogens, it also fits there. Right? But we need more there. So that's 2 to 2 to 3. So 2 to 2 to 3 for the integration. So that should be the structure. That is our prime candidate. And we really didn't even need to get to the hydrogen NMR before we could be virtually certain that that's what it was. Okay. You could, if you want further evidence, you might go back and look at the mass spectrum and try to figure out what these fragments are. 55 is probably a propyl plus a carbonyl. Let's try that. So a propyl is 43. No, wait. 43. Yeah. Yeah, I mean you can play around with it. I'm thinking it's just 12. So, yeah, I don't know. 55. It might, no. Well, anyway, it's not not super important. You might be able to figure it out with a little more time. But that's it.